Imagine this, a massive, superpowered telescope in space, pointed at a distant exoplanet, far beyond our reach. It's 124 light-years away, far enough to be out of our grasp but close enough for the most sophisticated technology ever built to take a deep look at its atmosphere. What the telescope reveals could change everything we know about the universe, and it does. This is the reality we are now facing thanks to the incredible James Webb Space Telescope, JWST. In 2023, this telescope revealed a potential biosignature on an exoplanet, K2-18b, that could be the key to answering one of humanity's oldest and most profound questions: are we alone in the universe? K2-18b is a planet located in the habitable zone of its star, where liquid water could exist on its surface. The planet has intrigued scientists for years due to its unique properties, and previous studies with the Hubble and Spitzer telescopes hinted that it could harbor water vapor in its atmosphere. But it was the Webb telescope that finally allowed scientists to take a closer, more detailed look at this distant world. Its remarkable infrared capabilities provided new insights that could point to the possibility of life. Webb's instruments detected spectral signatures of methane, carbon dioxide, and something else entirely, dimethyl sulfide, DMS, a sulfur-containing organic compound typically associated with life on Earth. On our planet, DMS is produced by marine organisms, such as plankton, and plays a crucial role in cloud formation and the characteristic sea smell we experience at the beach. It's also a key molecule in atmospheric chemistry. The detection of DMS on K2-18b would be an exciting, unprecedented find. If confirmed, it could be the first tangible evidence of extraterrestrial life. For years, we've wondered whether other planets could support life, but the challenge has always been to find hard evidence. While many exoplanets have been identified in the habitable zone where liquid water could exist, this is the first time that a molecule typically associated with biological activity has been detected on one. This discovery, while groundbreaking, comes with significant challenges. The signal of DMS was faint, and the data required specific analysis techniques to reveal its presence. This has led scientists to exercise caution. Could the compound have formed through non-biological processes? Could it have been produced by something other than life? These are important questions, and the scientific community is not jumping to conclusions. Instead, they are methodically working through the data, exploring every possible avenue before making any definitive claims. The exciting thing, however, is that the possibility of life elsewhere in the universe is more plausible now than ever before. To understand the significance of this discovery, it's important to look at the characteristics of K2-18b itself. This exoplanet is located in the habitable zone of its star, meaning it is at the right distance for liquid water to exist, just as Earth is in the habitable zone of our Sun. The surface temperatures of K2-18b are believed to be similar to those of Earth, and its atmosphere is thought to contain water vapor. Scientists have long speculated that planets like K2-18b, which may be covered in oceans, could be potential candidates for the existence of life. Oceans provide the right environment for the biochemical processes that life needs to thrive, and the presence of water vapor in the atmosphere is a positive sign that conditions might be conducive to life. However, even though the possibility of life is tantalizing, scientists remain cautious. The key to confirming whether K2-18b could harbor life lies in understanding the DMS signal. To do this, astronomers used advanced models to simulate the conditions on the planet. These models took into account the composition of the ocean and atmosphere, the processes by which DMS could be produced, and the ways in which it would break down in the atmosphere due to radiation from the planet's star. The results of these simulations were intriguing. They suggested that, under the right conditions, life forms on K2-18b could indeed produce detectable biosignatures like DMS. However, there's a catch. For DMS to accumulate in detectable concentrations on K2-18b, the production of this compound by extraterrestrial organisms would need to be significantly higher than on Earth. Specifically, the concentration of DMS would need to be at least 20 times higher than what we observe on Earth. The reason for this is that DMS is subject to photochemical decomposition. It breaks down when exposed to sunlight. The higher the concentration of DMS, the more likely it is to survive long enough in the atmosphere to be detected by our instruments. This introduces an important factor, the unique chemistry of ocean planets like K2-18b. On Earth, DMS is constantly being broken down by sunlight, but on a planet like K2-18b, with a potentially more robust ocean atmosphere, there could be a protective effect that shields the DMS from degradation. In other words, if the DMS concentration on K2-18b were high enough, it could accumulate in the atmosphere, creating a detectable biosignature. This protective effect could also help to preserve other potential biosignatures, offering a clue to the presence of life. Yet, while the models show that the detection of DMS is theoretically possible, the reality is that Webb's instruments have limitations. The signal of DMS detected by the near-infrared spectrometer (NIR-SPEC) on the James Webb Space Telescope was relatively weak and overlapped with the signal of methane, another common molecule found in planetary atmospheres. This makes it difficult to separate the two signals and confirm that the DMS detected on K2-18b is biologically produced. That's why scientists are now turning to Webb's mid-infrared spectrometer, MIRI, which operates in a different wavelength range that could provide a clearer, more definitive picture of the DMS signal. MIRI has the ability to detect molecules in the mid-infrared range between 9 and 13 microns, and it could potentially reveal new details about the chemical composition of K2-18b's atmosphere. MIRI has the technical capabilities to detect DMS in a way that NIR-SPEC couldn't, and experts are hopeful that this will bring us closer to confirming whether extraterrestrial life exists on this distant planet. While we wait for further data from Webb's MIRI instrument, it's worth considering the larger implications of these findings. The discovery of potential biosignatures on K2-18b opens up a whole new avenue of research. If life can exist on a planet 124 light-years away, then it is possible that life exists elsewhere in the universe, in places we have not yet discovered. It expands our understanding of where life might thrive. It also forces us to reconsider what we know about the conditions necessary for life. Could life arise in environments vastly different from our own? Could it exist in ways that we can't even begin to imagine? These are questions that the discovery of K2-18b's potential biosignature forces us to confront. Moreover, the implications of these findings go beyond just one exoplanet. The search for extraterrestrial life has been one of the driving forces behind the study of exoplanets for years. Thousands of planets have been discovered in the so-called habitable zone of their stars, where conditions might allow for liquid water to exist. Many of these planets are similar to Earth in size and composition, leading scientists to speculate that they could harbor life. However, until now, we've never had concrete evidence that life exists beyond our own planet. The detection of DMS on K2-18b could change that. If confirmed, it would represent the first real evidence that life, albeit in a different form, exists elsewhere in the universe. But K2-18b is not the only exoplanet that has sparked excitement in the scientific community. The James Webb Space Telescope has also been used to explore some of the oldest and most mysterious aspects of the universe. One of the most intriguing areas of study is the formation of the first stars in the universe. We know that the universe began with a Big Bang, a massive explosion that created the first particles of matter. But it wasn't until several 100 million years later that the first stars began to form. These early stars, known as population 3 stars, were made up of hydrogen and helium, the only elements that existed in the early universe. They were much larger and more massive than the stars we see today, and their explosions seeded the universe with heavier elements like carbon, oxygen, and iron. The formation of population 3 stars is one of the most important research questions in cosmology. Scientists have long wondered what these stars were like and how they contributed to the evolution of the universe. Until recently, detecting these stars has been incredibly difficult. They formed so long ago, and they were so far away, that our telescopes have struggled to resolve their light. However, thanks to the unprecedented capabilities of the James Webb Space Telescope, astronomers have been able to make significant strides in this area. Webb has already identified the spectral signature of population 3 stars in a galaxy located 13.4 billion light-years away, one of the earliest known galaxies in the universe. This discovery marks a major milestone in our understanding of the early universe and the formation of stars. The presence of population 3 stars is a significant clue to understanding the conditions that led to the formation of galaxies, stars, and eventually life. By studying these early stars, astronomers can learn more about the processes that shaped the universe. They can also investigate how the first elements were created and how they led to the formation of planets and life. The discovery of population 3 stars in the galaxy GN-Z11 is one of the most exciting results from the James Webb Space Telescope, and it promises to open new doors in the field of cosmology. As the James Webb Space Telescope continues to explore the distant reaches of the universe, it is revolutionizing our understanding of both the origins of life and the cosmos itself. With each new discovery, we move one step closer to answering the most fundamental questions about our existence. Where did we come from? Are we alone? What does the future hold? The discoveries from Webb promise to be some of the most significant in human history, and they are just the beginning of a new era of exploration.